So I'll go ahead and get started. What have we done the past couple of weeks? We've seen the integral forms of conservation of mass, conservation of momentum, conservation of angular momentum, as well as the energy equation, which we just saw last week. But if you remember what the conservation of mass was, we saw that the derivative with respect to time of an integral over a control volume, the density plus the mass moving across a controlled surface was equal to 0. So we have that the change of mass within a control volume plus the mass moving across that control volume's boundary had to sum equal to 0, or else we were violating conservation of mass. In most cases, this equation simplified down to pretty much rho q in had to equal rho q out, where rho is our density and q is our volumetric flow rate, which a lot of times for constant density flows simplified to the sum of VA in is equal to the sum of VA out. So that was what we got to see from this really, really complicated integral simplified down to something that was a little bit more manageable. Similarly, we were able to see that the conservation of momentum, which had some horrendous integral 2, often simplified down to the sum of the forces. So that was mass, this is momentum. Would be equal to the sum of rho A V V minus, or that's a vector equation, of rho A V V, and that was going to be out minus N. So when we were applying the conservation of momentum and the conservation of mass for a particular system, we would define the boundary of that system almost always based exclusively off of the problem statement. So, like if we were looking at a mixing chamber, where we would have inlets and an outlet, let's say, we would always look at our control volume to be defined by the boundaries of that mixing chamber. Or if we were looking at a pipe flow, we would look at the control volume in the pipe, right? So we would always use the boundaries of our system to kind of define our control volume. And that just made it a little bit easier to analyze. But that doesn't always have to be true. We can arbitrarily define any control volume based on anything that we want to base it off of. So let's just say, for example, we have some coordinate system. We'll have an x, y, and z coordinate system. Let's say that this entire coordinate system is submerged in water. Everything on this board is water. We can look at a stationary control volume defined by just an arbitrary cube in the middle of that fluid flow. So if this is all submerged and we have fluid flowing just in an arbitrary manner with some v, some velocity, where velocity can be defined by the components u, v, w. So this is a vector field in which we have a vector associated with the velocity at every x, y, and z location and at every time. So in this case, u, v, and w are all functions of x, y, z, and t. So if I'm going to look at, or if I'm going to apply conservation of mass to this cube, this completely submerged stationary control volume, I can apply this same sort of conservation of mass principles to this cube. I know that the rate of change points, delta x, delta z, and delta y. And I'll define the volume of this cube. It's going to be delta v is equal to delta x, delta y, delta z. So the rate of change in the control volume is going to be equal to the change of, so this control volume is already completely submerged. There's not being mass generated in that cube at all. It's already completely full. So the rate of change of the mass in this cube is only equal to the mass going in to delta V minus the mass going out of delta V. So that's how we can define the rate of change of the mass. Sorry, I didn't really write that. The rate of change of the mass in delta V. So, if that of course makes sense conceptually, that if we're going to change how much mass we have inside that cube, we either have to have mass that flows into that cube, or we have to have mass that flows out of that cube. But we want to represent this in a more stringent manner, I guess. We want to be able to derive this a little bit more precisely. So, if I look at the velocity field flowing through this cube, or this velocity field, we can break that down into x, y, and z components like we have here. So, in the x direction, we might have u that flows into the cube and out of the cube on the other side. We might have v that flows into the cube from the bottom and out of the cube to on the top. Similarly, we'll have w that's flowing from the back of the cube out the board to us. So if we want to look at how the rate of change of mass into the system can be derived, we need to break this equation down into kind of 3 components, and we'll derive each one separately. Okay, so the first one, how would we mathematically express the rate of change of mass within the control volume? So, what we're looking for is a rate of change of mass. So that's dm dt. And we can define that. Mass can be redefined as d dt of rho v. Because density times volume gets us the change of mass going in and out of that cube. So, in this cylindrical control volume, we know that dV dt is equal to 0. Because we're saying that control volume that we were specified here is not going to change with time. And that'll be a little bit important later on. Okay, so now let's look at the mass influx that's coming into that cube. And it's easy. We need to break it down into components so we can understand exactly what's going to be going on. So, what is the mass flowing in the x direction? We specified that was u. So if we wanted to go back through and we want to figure out what the mass flow through the cube is, we're going to go back to our simplified version of conservation of mass, where that just becomes v times a is our volumetric inflow, and we then multiply that by rho to get our mass inflow. So the rate of change of mass in the x direction, this is n to the control volume, is going to be equal to rho times v dot x hat times delta y delta z, which is going to be delta y delta z times rho u, where u is v dot x hat, or the x component of the velocity. And what I'm saying is that the mass flow, if we just imagine that all the flow is only going the x direction, The flow going through this cube would be the velocity in the x direction, or u, times this area. So that area times velocity is our volumetric flow, times rho is where we get our mass flow in the x direction through that cube. Similarly, you can define the mass flow in the y and z directions. And those are going to be rho times v dot y hat times the y direction is going to be flowing through this area, which is delta x, delta z. Which is going to be equal to delta x, delta z times rho v. Where v in this case is the y component of our velocity field. And our mass flow into the cube in the z direction is going to be rho times v dot z hat times delta x, delta y, which is going to be delta x, delta y, rho w. So that is going to be, so I kind of actually shaded the wrong portion of that cube. So, but the flow into the cube is going to be on this back side that we can't see. So this back side is going to be that area coming in, and coming out of the cube, it's going to be on this side of the cube. So there's actually, because the velocity field is going to change throughout this volume, because the velocity field is defined at every x, y, z location, the u component of the velocity might be greater at this side of the cube than it is at this side of the cube. So, in all these locations, if I define this back corner point as my x, y, z, these are all specified only at those back surfaces. So this is going to be at x is equal to x, at y is equal to y, and at z is equal to z. However, as we step through this cube, as we move from one side to the other side, our velocity field is going to change. And so our outflow of our mass might be different due to the step delta x that we took from the x location forward. So this is a very, very large cube. The flow here at this point might be greater in the x direction than it is as we move over here. And that way we might actually have a difference in how our flow is based from one surface of the cube to the other side of the cube. So the same sort of way that we define the mass influx, we need to define the mass outflux, which is going to be almost identical to this, but now we are changing our location. We're actually stepping forward from that XYZ location to this front location here, where the coordinates of the system are going to be x plus delta x, y plus delta y, z plus delta z. So the outflux can be defined just like we define the influx, but now we've changed our x directions, which means we've changed the values of u, v, and w. Because u, v, and w are not the same for all x, y, z locations. So our outflow in the x direction is going to be defined delta y, delta z times rho u, but now this is rho u at x is equal to x plus delta x. So we have moved one step forward, and we're having a different flux of mass through that opposite side. So the flux through this surface may not equal the flux through this surface, is what I'm trying to say. Similarly, the mass outflow in the y direction is going to be delta x, delta z times rho v at y is equal to y plus delta y. And my mass flow out in the z direction strange concept that we do when we deal with differentials. Does everyone follow me? How we're stepping forward from an XYZ location. That if I'm defining my inflow based on this surface, this surface, and this back surface, whereas I'm defining now it's just really complicated looking, but now I'm defining the outflow through this surface, and this surface. So, because this is a velocity field, the velocity going into this back surface may not be the same as the velocity leaving this front surface. So, that's the way it is, you're actually going to have different masses fluxing through different surfaces. So, that's what these equations are saying. And it just gets confusing when we look at it in differential form, because that's what we're trying to do. So I'll even mull that over while I erase this board. So we have this global equation that we're trying to set up right here. We have the change of mass in our control volume is equal to the mass coming into the control volume minus the mass coming out of the control volume. We have then solved for all three portions of that equation separately so that it's easier to, easier to break apart, easier to see. So we can now combine all these equations and look at them individually. And that's, if we look at that one side at a time, we have that the rate of change of mass in the control volume, which is going to be, over here we have dNdt, which is ddt of rho dot v. Because v is not changing with time, we can simplify that down to v dot d rho dt. So v I defined here as delta x, delta y, delta z. So the first part of our equation, which is the rate of change, is delta x, delta y, delta z, d rho dt. It's got to be equal to the mass coming into the system, which in this case we defined as, let's see, we have delta y, delta z times rho u at x is equal to x minus rho u at x is equal to x plus delta x. So now this is where we're beginning to see the volume coming in and the volume coming out are not going to be the same because rho u is going to have a different value at a different location in x. Similarly, we're going to have, it's also going to be this whole term plus delta, we're doing in the y direction, delta x, delta z times rho v at y is equal to y minus rho v at y is equal to y plus delta y. Plus delta x, delta y times rho w at z is equal to z minus rho w at z is equal to z plus delta z. So I have a very long, confusing equation, and we're going to do even more mathematical exercises to it. So I can then take this equation, and to both sides, I can divide. So for both sides, I'll just... I can divide by delta v, which is delta x, delta y, delta z. And then I can also take a limit as delta v goes to 0. So what we're doing is we're taking a derivative with respect to the volume in this case. But because we're dividing this side of the equation by delta V, we can just get dp dt, or the d rho dt. And this side, we actually end up taking a derivative with respect to x, with respect to y, and respect to z. For example, if we look at just the x component of this equation, what's the first thing we do? We're going to divide it by delta v. So now we end up getting delta x. So we're doing the limit as delta v goes to 0, but we'll get there in a second. So rho u at x is equal to x minus rho u at x is equal to x plus delta x. And I'm taking a limit of this entire thing as delta v goes to 0. But delta v is just delta x, delta y, delta z. I have none of delta y or delta z in my equation, so this is just a limit as delta x goes to 0 of this whole thing. So what does that end up being? That is a derivative, from definition, just straight up from Calc 1, that's a derivative of how rho u changes with respect to x. So I'm taking a minuscule step in the x direction, and I'm seeing the difference between those, and I'm taking a limit as delta x goes to 0. I wrote that wrong, which makes that confusing. Now it's a derivative. It wasn't a derivative before, but now it is. So now what we're doing is we're taking a derivative of rho u with respect to x. So, if I do that for each term individually in this entire equation, equal sign there, I get d rho dt. It's got to be equal. Okay, I didn't quite define that right. So this is going to be an x. This is an x plus delta x. So this is actually a negative of the derivative. So this entire term, I'll just write that. This entire term. So the limit, this limit and this dividing by delta v ends up just getting us negative del rho u del x. Is what it ends up getting. If this had been plus delta x, and then that had just been x, that would be a positive derivative. That's not how it is. It's x, and that's plus delta x. That's where we got the negative sign in front of our derivative. So now our entire conservation of mass equation is to be the change of mass coming into the system. I get del rho del t is equal to negative del rho u del x minus del rho v del y minus del rho w del z. Does everyone follow me before we are here? This is a big step. This is pretty important. So, simplifying that, moving all my terms to the same side, I end up getting that del rho del t plus del rho u del x plus del rho v del y plus del rho w del z is equal to 0. And this is your differential conservation of mass equation. This is a relatively important equation in fluid dynamics. If you do any upper level fluid dynamics past this class, you will definitely work with this conservation of mass form. But this is pretty complex looking. We can make it a little bit simpler depending on what fluid we're working with. So, if you look at this equation and you say that I'm going to set rho equal to a constant, which is a good approximation for a lot of fluids, not gases, but for most liquids, setting your rho to a constant density is a valid approximation. So, if I say rho is a constant, doesn't change with x, y, or z, this equation simplifies down to del u, del x, plus del v, del y, plus del w, del z is equal to 0. This term that you see right here, this del u, del x, del v, del y, del w, del z, is often called your dilation of your velocity field. What that does, what that pretty much says is that if this is not equal to 0, our control volume is going to be growing or shrinking because we are not, the mass flow coming into the control volume is not going to be the same as the mass flow leaving. So that's why it's often referred to as a dilation of your velocity field. So similarly for Cartesian coordinates, you can derive this equation for both cylindrical and spherical coordinate systems. This is all done in the e-book, so I'm not going to do it. But if you go look it up on the e-book, this form of the conservation of mass equation becomes del rho del t plus 1 over r del rho r vr del r plus 1 over r times del rho v theta del theta plus del rho vz del z. And in this coordinate system, that's all equal to 0. This is your coordinate system in which you have some r, you have some rotation angle theta, and you have some vertical location z. So you have your z-axis and your distance from the center, and then your velocity that's tangent, or the velocity that's rotating around your origin. But we're going to ignore that mostly for this lecture. Just understand that if you do have velocity fields giving in cylindrical coordinates, which you often do depending on the symmetry of your problem, you would apply this version and you can derive all these equations in any coordinate system that you choose. Okay, so let's work an example. So let's say I have some velocity field that's given by u is going to be equal to x squared y plus 4z. V is equal to something. You don't know what z is equal to. And w is equal to 6 minus x, y, z. We need to figure out what v is so this velocity field doesn't violate the conservation of mass. So that's what we're trying to do. We want to figure out what v's got to be. So if we assume it's an incompressible flow field, we can use this equation right here. And we know that du dx, which is going to be 2xy, plus dv dy, which we don't know, plus dw dz, which in this case there is no z in that, so that's 0, is got to be equal to 0. So from this I can see.
Isn't there a z?
Minus x, y.
X, y, z?
Yes, you're right. So that's going to be what? A minus xy. Okay, so that I can combine with here, that's an xy, so I can see that dv dy is going to be equal to xy. I can then integrate with respect to y, and I see that v is got to be equal to xy squared over 2 plus some function of x and z.
Wouldn't that be negative? Negative x, y?
Yes. So any v component of your velocity which takes this form, so any function of x, y, and z would satisfy conservation of mass. So that's going to be, you're probably going to have to work problems like that on both the test and the homework. Okay, let's see if I can find an eraser. Does anyone have any questions though? Does everyone kind of understand how we derive that equation? That's a relatively important equation, especially if you end up doing any further research into fluids or fluid dynamics. It kind of dictates a lot of different flows, so it's not something that you really want to ignore. It doesn't immediately have as many engineering applications as we've seen with those differential form of those equations, but a lot of numerical methods and research are going to solve these differential forms of conservation of mass. So now I'm going to introduce the concept of a stream function. So if we look at two-dimensional flow, we can classify two-dimensional flow by any v as a function of just u and v, assuming that there is no z component of velocity. So if I look at continuity for a two-dimensional flow, I know that du dx plus dv dy is equal to 0. So if I want to I can redefine how we look at velocity. If I say that there is some function which I will call psi, which is a function of x and y. I can then define u from this. I can say that u is equal to del psi del y plus, and I can say that v is equal to negative del psi del x. And all this is just a clever mathematical trick. Because if we then apply conservation of mass to this, I see that du dx now becomes del psi del y del x plus dv dy, which is minus del psi del y del x, is equal to 0, and this is true. So all we've done is we performed a mathematical trick that satisfies the conservation of mass. But what I can then do is I can then integrate u with respect to y and v with respect to x to find out what psi is. So this does several kind of important things. First, it reduces our number of unknowns from 2, in this case, which is u and v, which we don't know, to 1. Now we only have one function of x and y that we don't know. But it does turn our conservation of mass equation from a first-order equation to a second-order equation. So it does have some ramifications to it. Interestingly enough, if you then say, so psi is some function of x, y, if I set psi to a constant, that equation is a streamline for this flow field. So if I figure out what psi is some function of x and y, and I set that equal to some constant, that equation will be a streamline for the flow field. And any constant you pick will be a different streamline. So we'll go ahead and we'll work an example of that one too. So let's say I have a velocity field defined by v is equal to x comma negative y. So I can say from this definition right here, u is equal to d psi dy, so I have x. Well, first let's make sure that we have a valid flow field. We need to make sure that this satisfies the conservation of mass. So du dx plus dv dy is equal to 1 minus 1, which is equal to 0. So this is a valid flow. This does not violate conservation of mass. Now I want to find psi. So I can say that psi is defined such that u is equal to del psi del y, which is going to be equal to x. So psi is going to be equal to xy plus some function of x. I also know that v is equal to del psi del x, which is equal to negative y, or it's a negative del psi del x. So I get that psi is equal to xy plus some function, or not the same function, but a different function of y. Now, from differential equations, I know that these are both the same equation, so if I equate them to each other, I see that f of x has to be equal to g of y, and this is only possible when they both equal a constant. It's not really defined, it's just only possible when they both equal a constant. So now we know that psi is equal to x plus, or xy plus a constant. And any constant is still going to be a valid or a valid string function for this vector field, this velocity field. So what does that tell us? That allows us to help or kind of visualize what this two-dimensional flow would look like, because now we can set psi equal to a constant and solve for the streamlines at that location. So if I say that psi is equal to a constant, I know that psi minus c is equal to xy. So by picking psi to equal a constant, that's just going to be equal to some new constant. I'll call it c prime. And I can plug in various values of c prime to kind of visualize what this flow field will look like. If we do that, we end up getting that y is equal to c prime over x, and we get streamlines that look like this. Or I can plug in negative values of c prime, and I get streamlines that look like this. But these are streamlines. So these are just functions that we plotted, but because it has to deal with a velocity field, they have a direction associated with them. If fluid is flowing along these lines, it's only flowing one direction. To figure out what that is, I have to go back and look at what I defined my velocity field to be. So I know that whenever x is positive, my velocity field should be flowing in the positive x direction. So I can look at that, and I can say that this must be this direction. Also true, whenever x is on the negative side, it's flowing negative direction. It's flowing the same direction as the x side. So this is going to be flowing in this direction. Similarly, we'll see that it flows this way, and we can see that it flows this way. While there may not be any physical flows that you would expect to flow, exactly like this, if we look at the entire coordinate system, you can imagine how if we set our domain to only be positive x and y values, we could use this flow field to approximate flow around a corner. So if you're looking at maybe a channel that has some L shape to it, we could use this flow field to approximate this portion of that channel. So these are just a mathematical tool to kind of help us visualize how flows should look in real life. So no one has any questions? Nice. So, just like we could apply the same kind of conservation of mass principles to that small fluid element, we can also apply conservation of momentum principles to that fluid element. So, let's go ahead and we'll look at that same fluid element again, and we'll look at the forces acting on that fluid element. So if we have some coordinate system, and we have some stationary fluid element in the flow, what are the forces that we see acting on this particular fluid element? It's a lot easier to visualize if we take it one component at a time. So it's a submerged fluid element, so we have a pressure acting on this face and a pressure acting on this face, this back face here. So I'm looking in the x direction, I need to look at the forces acting here and the forces acting here, and equate those to the acceleration of that fluid element in the x direction. So I can say that acting on this, we have some surface area given by the same delta z, delta y, and we're going to have some stress acting on it times delta y, delta z. So this is a force. This is some stress acting over this surface element times the area of that element. Similarly, on this side of the element, we're going to have the same surface area times a different stress, because much like the velocity field, which will have a different value on one side of the cube as the other side of the cube, the stress will have a different value on both sides of the cube as well. So we'll call that, so it'll have the same value, sigma x, plus how that stress changes with respect to the x direction times the distance. So if this is changing 1 per every unit length times that unit length is going to give us the total change. So that's going to, I dropped some stuff here. So that's sigma x plus that times delta y delta z. So the force on this side of the cube is equal to the force on this side of the cube plus how that force changes with respect to the x direction times the translation in x. So that's just saying, if we're looking at a function, we're saying that if we look at the derivative at this location x, the location at some x plus delta x can be approximated as the derivative times that translation. So it's the same sort of argument that we've seen in math in the past. So if you remember kind of from solids, this is just one component of the stress that's acting on the surface. Anytime you have a three-dimensional stress state, you have 9 different components. So if I'm looking at the same differential volume, every face is going to have a stress normal to that face surface, a shear stress acting, I guess, parallel or perpendicular in one direction to that surface. That's a tau. Plus another one acting perpendicular to that. Similarly, this surface will have a stress acting this way, and this way. And this surface will have this way, and this way. And these we can define as sigma y, sigma, or I guess I use tau, sigma z, or excuse me, tau zx and tau zy. So we need to do a summation of forces in the x direction to figure out what our total net force is acting on this cube. And when we have acting on it, we have this one in the x direction, this one in the x direction, and this one in the x direction. We're going to take all those into account. So, to sum my forces in the x direction, I can see that delta y delta z plus sigma xx plus del sigma xx del x times delta x so I should say this is all equal to that plus delta x delta y times tau zy plus del tau zy del x times delta z plus delta x delta z times tau y. I did that wrong. This is zx. This is zx. Delta y, tau xy plus del tau yx del x times delta y. So this is just nothing more than this stress acting over this area, this stress acting over this area, and this stress acting over this area. So those are just forces acting on the fluid element. We can also have what are referred to as body forces, and this is something like gravity or an electric field. So if we somehow picked our coordinate system such that gravity has a component in the x direction, we also need to account for that too. And those are often, I'll just summarize that as gravity in this case. So gravity is what? The mass of the volume, mg, is how we usually define that. Well, we can just redefine that mass as a density times a volume. So we end up getting delta x, delta y, delta z times rho times the effective gravity in the x direction. And those are all of our forces acting in the x direction on this fluid element. So now we need to say that the forces acting on this element are what are causing any acceleration that we might see in the x direction. So we know that the sum of the forces in the x direction are equal to the mass of the element times the acceleration in the x direction. But we're in fluids, so acceleration is not as easy as it is in physics 1 or kinematics. We take into account that we're using the Eulerian viewpoint, and we have to use that version of acceleration that we derived earlier in the semester. So, we say that the sum of the forces in the x direction are equal to the mass times the volume. Well, the mass times the volume we have in this case is we have the mass, which is rho, times the volume, delta V, plus del U, del T, plus U, del X, plus V, del U, del Y, plus del U, W del U, del Z. And that was how we defined the acceleration in the x direction from the viewpoint that we're taking. We say that this needs to be equal to this. So we're going to do the same sort of thing that we did for conservation of mass. We're going to take both sides of the equation, and we're going to divide them by the differential volume, and we're going to take a limit as that differential volume goes to 0. So if I do that, what ends up happening? Well, on this side, my differential volume just gets divided off, and I take a limit as it goes to 0. Well, I have no components of that volume at all. So this side of the equation just becomes rho del u del t plus u del u del x plus v del u del y plus w del u del z. However, this side of the equation changes significantly. So let's just look at one of, actually, we should probably look at multiple components. So I'll look at it one piece at a time. So if we divide just this value by the entire volume element, I end up getting the limit as delta x goes to 0 of sigma xx plus del sigma xx del x delta x over delta x. Here I get, get this right. Yeah, so I do the same sort of thing here. Here I get the limit as delta y goes to 0 of sigma, or using tau zx plus del tau zx del so del x times, I have my delta z here, all over delta z. And this becomes, so this actually should be a limit as delta z goes to 0, because we're dividing off x and y. So the only component of the volume that we have left to turn to 0 is delta z. And this is going to be the limit as delta y goes to 0 times tau yx plus del tau yx del x times delta y all over delta y. So similarly, these are all just derivatives. So as it turns out, we get this side of the equation plus this side of the equation ends up getting us, and we divide this side by the volume, and we end up getting that this goes to rho gx. So we end up getting the final form of the x momentum equation becomes rho del u del t plus u del x plus v del u del y plus w del u del z is equal to del sigma x del x plus del tau y x del y plus del tau zx del z plus rho gx. So these we can solve for. These are not difficult. These are all functions of our velocity field. However, we need to figure out what to do with these particular components of the X momentum, because those aren't immediately obvious what they should be or how we deal with those stresses. So those stresses arise from two different sources that you have when you're working with a fluid field. We have the stresses working on that fluid element due to pressure, which is your hydrostatic pressure due to your depth in your water. And we also have the viscous stresses, or the stresses that we have that are dissipating energy due to that shearing layers of fluid between one another. So if we look at our hydrostatic stress, this is defined as these are all negative P's, these are all zeros. This is in tensor notation. What this is saying as much, just like we had the 9 stress elements acting on the fluid volume here before, we can define any stress state at all of sigma ij as sigma xx, tau xy, tau xz. Get rid of that. Tau. That's going to be x, y, sigma, y, y, tau, y, z, and tau, x, z, tau, y, z, sigma, z, z. Those are all the stresses acting on or during a stress state. Your hydrostatic stress, as if you think about it, if I looked at just that fluid element, what would be the stress acting on it due to pressure? So that's a Q. We only have 3 components because the pressure is always normal to the surface of the cube, right? So we have a P acting here, a P acting here, and a P acting here. So all these shear terms that we had before are non-existent for pressure. We just have pressure acting only normal to that surface. So we have one of our 2 components of our stresses here is going to be the hydrostatic pressure, defined by this in tensor notation. Just all it means that all the pressures are normal to the surface of the cube. We also said the other component of those stresses were the viscous stresses acting on that cube. So how do we define those viscous stresses? So we need to go back to early in the semester when we first defined viscosity. When we first defined viscosity, we defined it for the case in which we had a stationary plate and a moving plate that was moving with a velocity u. And we said that the velocity distribution in this case was linear, going from a value of 0 to some positive value u. And for Newtonian fluids, that velocity gradient is linear. We said in this case that the viscosity was defined as tau is equal to mu del u del y, or in this case, because it was one-dimensional, they were actually complete derivatives, not partial derivatives. So this was actually a simplification of how we define viscosity. We define viscosity for 3 dimensions based off multiple shearing, because we could also have shearing in this plane. This is a one-dimensional flow, so we only have one velocity gradient. So this was actually a simplification of tau xy, which is equal to tau yx is equal to mu del u del y plus del v del x. But because we didn't have any vertical portion of this flow, del v del x went to 0 and it's simplified in this case. So you can actually go ahead and you can derive the entire viscosity tensor for, I guess, pretty much incompressible only. We can derive the viscosity tensor as tau ij